input is not steady. So the input is continuously changing, and the dynamic response of an instrument to an input signal is typically modeled in terms. So now we have to worry about that if a signal, if the input signal suddenly changes from some value to some value, how is the output signal going to change? So we are not only concerned with the new steady state value that the output signal will achieve, but we are also concerned with how it is going to achieve that over time. So when we talk about such characteristics, we talk about the dynamic characteristics of instruments. So accordingly, we have various kinds of instruments. So we start with the simplest, which is the zero order instrument, whose characteristic is given by y equal to kx. So it is assumed that for the kind of inputs that are relevant to that sensor, the output is instantaneously equal to the input. So it's like a resistance, you just apply a voltage, you immediately get a current. So the input output ratio is linear, and this linearity exists from instant to instant, right? So it is for such instruments there is no dynamics, and the static characteristic is the only characteristic that you need to see. So such instruments are called zero order instruments. For example, typically, a potentiometer. I was talking about a resistance, right? So a potentiometer is nothing but a resistance. So for a potentiometer, the position signals, potentiometers typically measure position, so the potentiometer will be connected to this variable point. So as the variable point moves, the voltage that you will get will be directly proportional to the position, right? So in this case there will be instant to instant, and since the position is actually a mechanical variable, so therefore there is not going to be too fast a movement. So as far as the electrical behavior is so fast compared to that you can just assume it to be a pure resistance, and then you have what is known as a zero order characteristics. So the output voltage will be directly proportional to the displacement theta. Let us say angular displacement. In this case, if potentiometers can be angular as well as linear. So there is a sensitivity called of the potentiometer is volts per radian. On the other hand, there are some kinds of instruments where if the input changes suddenly, the output cannot change suddenly. The output takes some time to rise. For example, let's say temperature measuring instruments. For example, thermocouple. Actually, a thermocouple is typically, as you will see, it is not wherever it is making the measurement of the temperature. Maybe it's steam. Then the bare thermocouple is actually not inserted into the steam, because that will damage the sensor. It will degrade fast. So it is actually put inside a tube. So you can imagine that even if there is a temperature change outside that tube, which is called a thermo well, so it's a tube, inside that you have the thermocouple. So even if your your environmental temperature which you are trying to sense, even if it changes, some time will be required for this temperature to actually flow through that is, there has to be heat flow through the insides of the thermo well into the thermocouple junction before an EMF can be developed. So because of the thermal properties of this thermo well, there is going to be some time required. So even if you suddenly fill this space with, let us say, steam, the temperature of the junction of the thermocouple will not instantaneously be equal to the temperature of the steam, but it will slowly rise, right? So for such transducers, we have a first order instrument character, first order or second order. So that will depend on the modeling of the thermocouple. But so typically first order instruments are transducers that contain a single storage element and can be modeled of first order. So for such cases, the output value actually obeys some kind of a differential equation which is of this type, and where tau is called the time constant of the system. So if tau is larger, then the system slowly rises, while if tau is short, then the system is fast. So we can easily compute the response of a sensor whose input is a step input. So let us try to characterize the response of this kind of a sensor to various kinds of changing inputs. So the first, so these are two examples, Mercurian glass thermometer and thermocouple in a thermowell. So if you have a step input, so the first kind of input that we consider is a step input. So step input means it is at 0 and then suddenly it rises. So at t is equal to 0, the input is 1, suppose. So then we can compute that the time response or yt is going to be such a function of time. So the graph will show what kind of a function it is. So you see that it will gradually rise and then it will become 1. So if you have a large tau, it will rise slowly. If you have a small tau, it will rise fast. So this is tau decreasing, right? On the other hand, as we all know, I mean, the response to a dynamic sensor to arbitrary inputs is of interest, because if such a sensor is actually put in a control loop, all kinds of, it is not going to be regular as a step input. So we sometimes, since we know that any arbitrary waveform, most arbitrary waveforms can be thought of as a sum of sinusoids, sine and cosine waves. So it is very useful to actually characterize the behavior, that is the response of the instrument to a sinusoid of different frequencies. So this is called a frequency response, and this is very important for an instrument. So if we have a sinusoid, so this is my instrument. I am applying an I sin omega t. Typically what will happen is that if the instrument is supposed to be linear, then you will get, as output also you will get a sine wave, but that sine wave magnitude will be higher, will be different from the magnitude of the input wave, and it will also develop a phase lag. So it is this, so we actually try to study two things. Since the frequency is going to remain constant, so the frequency need not be studied, it is the input frequency itself. But the ratio between the output magnitude and the input magnitude, which we call the gain, and the phase lag, these are the two things that we typically characterize. So this is a mathematical solution. So for example, the gain over different values of frequency actually varies like this. So you can understand that if the frequency is too low, then the gain of that is 1, because so the frequency is too low means you are giving a slow sinusoid, which means that the instrument can always come to steady state and it can get the value of the input. On the other hand, as the input frequency increases, so before the output of the instrument can really rise, the input changes. So the output of the instrument can never rise enough, and therefore the gain falls. So this is the frequency characteristic of an instrument. Similarly, if you have a phase plot, then it turns out that as you go for higher and higher frequencies, the phase lag increases, and the maximum phase lag possible for a first order system can be 90 degrees. So it will gradually approach 90 degrees.